A patient arrives in the emergency department with sudden severe flank pain. Inside their urinary tract, jagged crystalline structures are actively precipitating out of solution, aggregating into hard masses that obstruct normal flow. While immediate care focuses on pain management and renal function, long-term resolution requires identifying the specific chemical makeup of the offending stone. Medical education often reduces this identification process to a list of disconnected facts, isolated chemical properties, and trivia that students are expected to memorize. Recalling a flat list of facts is a fragile strategy under clinical pressure, where the cognitive load can cause disconnected memory hooks to fail. A more resilient approach involves translating linguistic memory hooks into a rigid spatial diagnostic algorithm. This map must account for the 4 primary etiologies: calcium oxalate, calcium phosphate, uric acid, and struvite. Mastering these 4 types involves navigating a deterministic hierarchy of clinical variables to reach a logical conclusion. To build this spatial algorithm, we start from first principles. We begin with a blank slate and establish strict rules, one by one. Our baseline architecture is 4 identical pillars. Every stone type will reside in one of these positions. Calcium oxalate takes the first position. Calcium phosphate takes the second. The third is reserved for uric acid. Struvite occupies the final slot. Right now, these are just 4 empty placeholders. To make them clinically actionable, we must run them through a systematic series of diagnostic filters. In diagnostics, when specific data is missing, statistical prevalence guides the initial assumption. Among all renal stones, calcium oxalate holds the overwhelming statistical majority. We lock this statistic in place using a simple heuristic: calcium is king. Board examiners frequently rely on this strict K equals K linguistic rule to anchor the prevalence data. We map this probability permanently onto our baseline architecture. By placing a crown on the first pillar, we denote calcium oxalate as the most likely default etiology. While calcium phosphate shares the elemental base, oxalate is the primary driver of this statistical dominance. A clinician uses this fact to frame their differential. Before a single lab test or imaging order comes back, the mathematical odds point directly to oxalate. Probability provides a vital anchor, but it remains a starting point. We require radiographic evidence to narrow the field. The standard KUB X-ray, capturing the kidney, ureter, and bladder, serves as the primary filter in our diagnostic algorithm. Dense chemical structures absorb the radiation from the scanner. Because the beams cannot pass through the stone, it casts a shadow, appearing white on the film. This is radioopacity. When we sweep the X-ray filter across our structural model, we introduce a crucial bifurcation in the data. As the beam passes over the 4 etiologies, one fails to cast a shadow. This specific radiolucent outlier is uric acid. The chemical etiology maps directly to its imaging profile. Uric acid is unseen. An invisible stone on a radiograph indicates a uric acid etiology. By definition, this establishes the inverse rule. Calcium oxalate, calcium phosphate, and struvite are all strictly radioopaque. This radiographic check splits our matrix into 2 actionable categories, visible and invisible. The presence or absence of a shadow on a radiograph eliminates 75% of the differential possibilities. This leaves us with a specific clinical blind spot. We have 3 visible stones, and statistical prevalence cannot distinguish between them. We resolve this using our final diagnostic filter, morphology. We must observe the physical shape and growth pattern of the calculus itself. In some rare and severe cases, a specific stone's growth mechanism takes on an aggressive, highly complex, and branching physical architecture. Inside the human anatomy, this stone precipitates until it fills the entire renal pelvis, extending outward into the calyces. Struvite is the exclusive etiology capable of producing this massive, cast-forming growth pattern. We map its morphological extremity onto our mental framework. It provides a linguistic symmetry for rapid recall. The S in Struvite stands for Staghorn. Identifying a Staghorn calculus overrides the probability heuristic established earlier. The physical shape dictates the diagnosis, regardless of statistical likelihood. This massive structure stands in stark contrast to the small, distinct shapes typical of calcium-based stones. When imaging reveals radioopaque targets, macroscopic morphology acts as the definitive diagnostic tiebreaker. We can now assemble the final mental model, converting our 4 isolated pillars into an interconnected flowchart. The primary y-axis is the radiograph check. We split incoming data into either visible or unseen pathways. Following the unseen path leads to a singular conclusion: uric acid. Tracing the visible path down brings us to the secondary x-axis, where we apply the morphological check. If the imaging shows a massive, branching cast, we reach the Struvite endpoint via the Staghorn rule. If the morphology is standard, we follow the King heuristic, pointing to calcium oxalate as the most probable etiology. This sequence creates a high-speed routing mechanism suitable for both clinical exams and live triage. True clinical mastery is achieved by organizing clinical variables into a systematic framework for decision-making.